Welcome to today's video. Today I'm going to give a brief general introduction to Laurent series. Now, a Laurent series, if you have a function f, a Laurent series is when you do a power series expansion for f, but when you're allowed to include negative powers. So it's slightly different to a Taylor series, because when you do a Taylor series, you only include non-negative powers. So for example, if I take some function, like the exponential function, let's say, e to the z, and if I was to find its Taylor series, well, this one is well known. The Taylor series for the exponential function is 1 plus z squared on 2 factorial plus z cubed on 3 factorial, etc., etc. As you can see, in this power series expansion, there are no negative powers involved, right? That's the difference between a Taylor series and a Laurent series. In a Laurent series, you are allowed to include negative powers in your power series expansion. So Laurent series is not some very abstract foreign concept. It's just taking the idea of a Taylor series and extending it to something where you are allowed to include negative powers. That's pretty much all it is. Now, let me write the formal result of for Laurent series. Okay, so the formal result is as follows. Suppose you have a function f, which is analytic in some annulus, so some region like this. Capital R. So actually maybe I should draw what this annulus looks like. So you have a point z0. In most cases, we're going to consider the case where f is not defined as z0, or in other words, z0 is a singularity. I'll explain what that means later on. Anyway, you have a point z0, and around z0, there's a circle of radius little r. So something like this, and this has radius r, and then there's also a circle of bigger radius, which I'll call capital R. Okay, so this distance here is capital R. And in this result which I'm about to give, what we're assuming that the function f is analytic between these two circles. So it's analytic in this region which I am shading in right now. Right? We call that an annulus. Okay, so f is analytic in this region. If that's the case, then I can write a power series expansion for f at the point z0, or in other words, a Laurent series. So then Laurent series at z equals z0 is given by, looks something like this. F of z equals the sum from infinity, well, starts from negative infinity going all the way to infinity, some coefficient which I'll call Cn, times z minus z0 to the n. Okay, this is what's called the Laurent series for f at z equals z0. And notice that this expression here includes negative powers. So note the presence of negative powers. So that's pretty much all it is, right? It's just an extension of the Taylor series. It's when you have a power series expansion, but when you can include negative powers as well. Now you may be wondering, well, what is that Cn? What is that coefficient Cn given by? Do we have an expression for it? Well, yes, we do. Cn in this case, we have the following formula for Cn. It's defined to be 1 over 2 pi I, and then it's a contour integral around C of f of z minus z naught to the power of n plus 1 dz. Okay. Now what is C? C is any closed contour that lies in that annulus, going in the positive anticlockwise direction. So if I draw some random contour lying in the shaded region, C can be something like that, right? Whoops. So this is C. So you have that power series expansion, and the coefficient Cn for any n is given by that contour integral, where you can take C to be any closed contour lying in the annulus. That's pretty much it for Laurent series. Now, as you can see, this is a really nice result, but obviously it's a little bit too hardcore for everyday use, as in I don't want to calculate infinite amounts of contour integrals all day, right? So in practical applications, we don't usually find the Laurent series using this formula. Actually, what we do, we take a Taylor series and then we manipulate it to find the Laurent series. That's often the standard approach. So let me give you an example. Let's find the Laurent series of f of z equals e to the z on z cubed. Now, sometimes the question will say, for example, find the Laurent series of f of z at z equals 0. That's the point of interest in this case, because f is undefined at 0. Or instead of saying at z equals 0, they may word the question like this. They may say, find the Laurent series that is valid in the region modulus of z is greater than 0. So questions are often worded in one of these two ways. They'll either say find the Laurent series at a point, or equivalently find the Laurent series in some annulus. In this case, because the function doesn't have two singularities, it doesn't have two or more singularities, I don't have an annulus like the one I drew in the previous case. I'm just considering the case when the modulus of z is greater than 0. In any case, whichever way the question is worded, they both mean the same things. Now, how do you actually do this question? Well, we know from our Taylor series that e to the z can be written as the sum from n equals 0 to infinity of z to the n on n factorial. And here, because I'm considering the case when the modulus of z is greater than 0, or in other words, since z is not equal to 0, I can divide through by z cubed. And this is going to give me z to the n minus 3 on n factorial. And that's it. That's the Laurent series. It's really that easy. It's not supposed to be very complicated. So as you can see here, why is this a Laurent series? Well, this one contains negative powers of z. if I was to write the first few terms out of this one, I would get 1 on z cubed plus 1 on z squared plus 1 on 2 factorial z plus, and then the rest would be the positive powers, I guess, or the non-negative powers. So they'd start from n equals 3. So as you can see, this power series expansion contains some negative powers of z, and that's why it's called the Laurent series. And one of the things I should mention is that this component of the Laurent series that contains negative powers, we call this the principal part of the Laurent series. And it's actually a very important skill to be able to find the principal part of a Laurent series. Or actually, not even to find the principal part, just to be able to figure out how many terms are going to be in the principal part. That's going to play a really important role later on when we speak about residues. So I'll do an example about the principal part as well, because it will be important later on. So let me see. So as an example, I want to find the principal part of f of z equals z to the power of 10 on z minus 5 squared at z equals 5. Okay, so what does this question mean? I'm not interested in the entire Laurent series for the function f. I want to find the part of the Laurent series for f at z equals 5 and the part which contains negative powers. That's all I want. So how do you go about this question? What you can do, you can say let g of z equal the numerator z to the power of 10. Okay? Well, here, as you can see, g is going to be an entire function, by that I mean it's going to be analytic everywhere. So g has Taylor series expansion. Because g is entire, it's going to have Taylor series expansion. So formula for Taylor series is sum from n equals 0 to infinity. And I'm going to do the Taylor series at z equals 5. So the formula becomes nth derivative at 5 on n factorial times z minus 5 to the n. Okay? And if I write the first few terms of this one, so first term would be g of 5. Second term would be g dash 5 z minus 5. Third term would be g double dash of 5 over 2 factorial z minus 5 squared. And going on with that pattern, I can see the fourth term would be third derivative 5, 3 factorial z minus 5 cubed, etc., etc., right? Goes on forever. Now, when modulus of z minus 5 is greater than 0, or in other words, when z doesn't equal 5, I can divide through by z minus 5, right? And if I divide g by z minus 5, I should say z minus 5 squared actually. When I divide g by z minus 5 squared, I get exactly f of z, right? So if I divide by z minus 5 squared, the left becomes f of z. Now the right, let's have a look. It's going to become g on 5 on z minus 5 squared plus g dash 5 on z minus 5 plus g double dash of 5 on 2 factorial. Actually, there's not going to be anything in front of that constant. because the z minus 5 squared is going to cancel the z minus 5 squared. But the next one is going to become z minus 5 instead of z minus 5 to the power of 3. And again, that will go on forever. So now, as you can see, I have a Taylor series. I have a power series for f that contains negative powers. And because I just want the principal part of this Laurent series, I just want this part here. This is the principal part because this is where the negative powers are, right? So now, maybe I'm out of room a little bit. Maybe if I continue up here, I can see that g of 5 is equal to, well, it's going to be 5 to the power of 10, since g is z to the power of 10. And g dash 5, so derivative of z to the 10 is 10z to the 9. If I evaluate this at 5, I get 10 times 5 to the 9. So therefore, principal part is going to equal g of 5, which is 5 to the 10 on z minus 5 squared, plus g dash 5, which is 10 times 5 to the 9 on z minus 5. And that's how you find the principal part of a Laurent series. So that's pretty much it, actually. That's a very general introduction to Laurent series. Take-home message is, idea of a Laurent series, nothing to really freak out about. It's just an extension of a Taylor series where you can have negative powers. An important part of Laurent series is finding the principal part, or the part which includes negative powers. And in both cases, the main strategy is to just take a well-known Taylor series and manipulate it. So that's it for this video.